Hello everyone, welcome to my your programming club. Today we will be solving another daily lead code problem, and the problem's name is maximum magnetic force between two balls. Okay, so the problem statement goes like this: you are on a in the universe on the particular Earth number, which is Earth C137. Okay, Rick discovered a special form of magnetic force between two balls if they are put in his newly invented baskets. Okay, so Rick has n empty baskets initially, and the ith basket is uh, present at the position at the in position represented by the ith index of this positions array. Okay, and there is his friend Morty, you can say, and has m balls and needs to distribute the balls into the baskets of Rick such that the minimum magnetic force between any two balls is maximum. Okay, so Rick stated that the magnetic force between two balls is at positions x and y is the absolute difference of between their positions. Okay, so in a way the problem statement is asking to place balls such that the difference between two consecutive balls is maximum possible. Okay, and given the integer array position and the number of balls m, return the required force or the maximum minimum magnetic force possible. Okay, minimum magnetic force, so that at least between every force this much magnetic force is there, and that magnetic force should be maximum. When this will happen, this will only happen when between two consecutive balls they are at the maximum distance between from each other possible, such that all the balls can be placed. Okay, so these are the constraints. So also let's have a look at the constraints given by the problem statement also. According to the problem statement, there are 10 raised to power 5 order of number of baskets, and the positions of the baskets will be ranging from 1 to 10 raised to power 9, and all the integers in the position array that we will be given to you will be distinct. So no two empty baskets will be placed at the same position. Okay, and the number of balls will be ranging from 2 to the number of baskets. Okay, so these are the constraints given by the problem statement. So let's take this example and take it to the board and try to understand what the problem statement is asking us to do. Although I have already explained you that we have to place all the balls such that the minimum difference between two consecutive balls is maximum. Okay, so let's take the data also that is given to us. So this is the data. So according to this data, these are the positions. Let me change color here. So these are the positions at which balls are placed. Empty baskets are placed. Okay, and then you have to place m balls. Okay, number of balls. So you have to place them such that the minimum difference between or the difference between minimum difference between any two adjacent balls is maximum. Okay, so here the difference was, as you can see, 4 minus 1, which was 3, and here the difference was 7 minus 4, which is again 3, and the difference between these two, the first one and the very last one, will be 7 minus 1 is equal to 6. So what is the minimum? Minimum is 3. We have to maximize this minimum. Okay, So a very intuitive way of doing it is, first of all, you need to check what is the range between which our answer can lie. Okay, so there can be a situation that all the balls, the number of balls are so large or equal to the number of positions that you have to place balls in every basket. In that case, the total distance between two adjacent balls will be, minimum total distance between minimum distance between any two adjacent balls will be 0. Okay, 0 distance. So from 0 distance to, let's say, there were only two balls to be placed. Instead of these balls being placed in every bin, you were required to only place uh, two balls, and let's say it was empty. Okay, then only these two balls will be placed here. So maximum difference can be 7. Okay, 7 minus 1 is equal to 6. Okay, so minimum minus maximum, you can say, in a way. So the least distance can be 0, and the maximum can be, if you take, do not consider this minimum value, then you can say max of positions. Okay, between this range, your answer will be lying. Okay, so this will be your answers range. So what you can do here is, you can try picking, you can traverse this range from left to right direction, and for each there will be some candidates for the answer. Okay, candidates for answer. You will check for, let's say we are at X position in the range, then we will check, can minimum maximum magnetic force between two adjacent balls be X or not. Okay, for that what we will do, first of all, we will have two variables, ball count. Okay, let's say M is required balls. Okay, so ball count will be initially 0, and then there will be one previous position value. It is the value at which you have inserted the previous ball. So previous position will be initially set to the value which is not in the range, the constraint. So 0 is not there, so you can take it to be 0. Okay, so then you will traverse this positions array that is given to you. Okay, before that, you will be wanting to sort this array. Okay, in order to have efficient running of this particular check, for x2, x is the proposed maximum force, minimum maximum force. Okay, you can say. So you are checking it whether it's possible or not, checking its feasibility. Then you will be traversing your positions array, the sorted positions array, from left to right direction. So this is the positions array. So if the previous position is the 0th position, okay, or it is the case that the distance between the previous position and the current position being visited, so let's say this is the current position. So current position minus previous position is greater than or equal to this proposed, let's say, force. Then in that case, if either of these two conditions are satisfying, okay, in that case you can say that we can insert the ball here. Okay, and we will incrementing the ball count. Okay, and also we will be updating the previous position because we have just inserted a ball. Okay, update our previous position. So this is how we will keep continuing, and when we are done traversing this positions array, then at last we will check the condition that ball count should be greater than or equal to the required balls to be placed. Okay, if it is so, then you can very well say that okay, it is possible for this proposed value to be the maximum minimum force possible. Okay, maximum minimum force possible. Okay, so in that case what you will do, you will check further. Okay, you will check for the larger force because you have to maximize it. Okay, so even for traversing this much size array, what is the maximum possible value of the position? It is 10 raised to power 9. So what, and the minimum is 1. So 1 to 10 raised to power 9 will take you, even for traversing this range only, order of 10 raised to power 9 operations. Okay, and there is a operation limit generally for the online judges when you are submitting your solution to online judges like LeetCode. Okay, so it is order of 10 raised to power 8 operations limit. So this, the number of operations that we will be requiring will be exceeding this limit. Okay, so it is exceeding. That's why this will give us TLE, time limit exceeded, and our solution will not be accepted. So we need to optimize this somehow. Okay, now the question arises how we are going to optimize it. So this checking part we cannot optimize because it's just linear, right? And it has to be done in order to check the feasibility of the proposed maximum minimum force. Okay, so we cannot help in reducing the time complexity at this step, but we can surely reduce the time complexity here while we are traversing the range, checking for the next possible candidate. Okay, candidate for answer, or the proposed candidate for answer can be checked with the help of, instead of searching linearly, we can use a technique which is called binary search. Okay, so those of you who are hearing this term for the very first time, I will provide the link of an article which you can explore, and it will make you understand what is binary search, when and how to use it, what are the journal templates that are used in binary search. Okay, and all these things. So once you have knowledge of binary search, then we can proceed further. What binary search essentially does that, let's say there is some search space was from 1 to 10 raised to power 9, let's say. So in each iteration of binary search, okay, you will reduce the search space to half. So for a search space of size n, let's say this was of size n. Okay, the whole size was n. Overall time complexity of binary search will be log of n. Okay, so it will be log of 10 raised to power 9. Okay, so even if you calculate it, it will not be that large. Okay, so it will be around, somewhat around, you can say 40 or 60, but you can definitely check it out. Okay, so let's check. Okay, it's around 30, as you can see. So from 10 raised to power 9 to order of 30, you can say around order of 30, or even if you take some loose upper bound of 60 also, then also it will be fine. Okay, and now you are a possible candidate for proposed force, candidate for answer, you can say, will be coming in order of log of n. Okay, and you can say 10 raised to power 9. And you can see that the part that we were using to check its feasibility will always be running order of size of positions array. Okay, so let's say the size of the positions array is n as per the problem statement. So the overall time complexity of this one will be order of n into maximum value of positions array. Okay, log of this whole taken as log. So order of n into log of maximum value of positions array. So this much will be the time complexity. And if you see what is the maximum range for n, it is 10 raised to power 5. And what will be the this value? As we discussed, it will be around 30. If you take it 60 also, then it will be also fine. So the overall time complexity or the number of operations comes around these number of operations, and these are lesser than the operation limit, which is order of 10 raised to power 8. Okay, so your solution will be accepted. So this is the whole idea. And for the binary search part and the implementation parts, let's have a quick look at the implementation. Let me take the code to the board, and let's take a fresh slide. So this is the code that will be implementing this binary search. So this is the part where we have implemented the binary search. Okay, so as we discussed, our search space will be ranging from left, which can be 0, to right, which is the maximum value in the positions array. So this is our search space. Search space is nothing but possible candidates for answer. Although it's just a fancy term, this time this kind of implementation or use of or application of binary search is called binary search on answer. Okay, because you this is the range for the between which your answers will be in from left to right. So this is the range for your answers. Okay, on which binary search is applied. Okay, at each iteration of this binary search, it will propose you some value of the force that you have to check its feasibility. Okay, so proposed value will be the mid value between the range, current range, and this is just a standard binary search till here. Okay, then this is where the interesting part comes in, the part where we will decide how we will be reducing the search space. How to reduce search space. Okay, as we talked that binary search will be taking this mid value and calling this proposed force. Okay, so let's say this was the mid value. Then if let's say it is good that this proposed force is possible, how is it possible? As I discussed, the ball count and the previous position will be the variables. Here I have taken the previous position initially to -1. If the previous position is -1, it means that you have not inserted any ball into the baskets or the bins that are uh, given by the rig. And or if it is the case that the distance between the previous position and the current position is greater than or equal to the proposed force, then we are safe to say that we can place one ball in this current position of the basket or bin, and in that case we will increase the ball count. And your previous position on which the insertion was made will also be updated. And at last, when you are done traversing this whole positions array, you will check for this condition that ball count is greater than or equal to the required balls. Okay, if it is so, you will say that okay, you have made a good proposition for the force or the possible answer. Go ahead and try for a larger force. Okay, so to try for a larger force, you might want to you will be wanting to actually to increase your range from left hand side. So it will left will shift to just one position ahead of this proposed force. So it will be proposed force plus 1. Okay, so this is that scenario. And if let's say we have proposed a force that is very much higher than the feasible force, then you can say that we will be wanting to reduce our proposed force in that case. Okay, in that case your right boundary will be shifting to this position. Okay, which is nothing but proposed force minus 1. Okay, so your search space will be this much portion. Okay, reduced from this entire one. Okay, so this is how binary search will work out here. And time complexity I have already told you. Okay, and maximum value, you know although this value will be order of, because of the sorting it will require order of n log n. Okay, but still, as compared to this order of n into log of maximum value, which is 10 raised to power 9, order of 10 raised to power 9, it will be still greater than that. So you can say that the overall time complexity will still be, as we discussed, n into log of. So this one can be ignored. So overall time complexity, let me take it to a fresh slide for the complexity discussion. So the time complexity will be order of order of n into log of maximum value of positions array. Okay, space complexity wise, as you have seen that we are not using any extra space here. Okay, so it will be constant order of 1. So this is how we will be solving this particular problem. Binary search is a very good technique to master, and it is very good to know that when and how this technique can come in handy for solving solution problems like this. Okay, so in which you can binary search around answers. Okay, so I hope this solution video added some value to your journey of honing your DSA skills. And if you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. Till then, keep solving problems, keep practicing. I will see you in the next video. Thank you for watching.